Next, we are going to discuss the role of energy in solution formation. When we take a solute and we dissolve it in a solvent, this does not involve a chemical transformation. So imagine that we're making a saltwater solution. If we start with solid sodium chloride and we dissolve it in some water, which would be our solvent in this case, all that's going to happen is the solid sodium chloride is going to break up and dissociate into aqueous sodium ions with a +1 charge and aqueous chloride anions with a -1 charge. Some energy is going to be required to overcome those intermolecular forces that are holding together the water molecules, and that is hydrogen bonding in water. So what's going to happen is the sodium ion, which has a +1 charge, will become solvated or hydrated. It'll be surrounded by the water molecules. But how those water molecules orient themselves is going to be very important. The sodium ion will be surrounded by the partial negatively charged oxygen of the water. So oxygen is more electronegative than hydrogen, therefore we know it develops a partial negative charge, whereas the hydrogens will develop a partial positive charge. So we have a partial negative charge on each oxygen and a partial positive charge on each hydrogen. Whereas with our chloride anion that's formed when it's dissolved is going to be surrounded by the hydrogen of the water. And that's because the charges are opposite. So the partial negative on the oxygen will be true still, and hydrogen will have a partial positive, but that's going to want to be next to the chloride, which has a full negative charge on it. And this process is called solvation or hydration when the solvent is in particularly water. Sometimes when we make a solution, the process can be endothermic or it can be exothermic, depending upon the nature of the solute and the solvent. So recall that an endothermic process is one where the enthalpy change overall is a positive value, whereas an exothermic process is one where the enthalpy change overall is a negative value. Let's first talk about forming a solution that is an endothermic process, meaning overall the delta H or enthalpy of the solution formation is a positive value. If you imagine you start with an individual solute in a container and an individual solvent in a container, there's going to be some energy required to take that individual solvent and break apart the intermolecular forces of attraction. So that's going to require an increase in the energy to break those IMFs. Same thing is true with the solute. If we're imagining the solute as a solid, those intermolecular forces of attraction holding it together could be even stronger. So it's going to require even more energy to break apart those particles and have them separated. Once we reach our separated particles and the intermolecular forces of attraction between the solute and the solvent separately have been broken, when we form the solution and we mix those separated particles together, some amount of energy is going to be released. However much energy is released during this process will determine if the overall process is endothermic or exothermic. In this example, we can see that the amount of energy released is less than the amount of energy that was required to break apart the individual intermolecular forces in the solute and the solvent. Therefore, the difference between the two of them is a positive value, and we have an overall endothermic process, or delta H of solution is equal to a positive value. Another way that we can think about this is if we have the solute and the solvent individually, and then we're going to make the solution on the product side. For an endothermic process, what that means is heat is a reactant. So we can write heat over here on the left-hand side of our equation. And what's going to happen is if we warm up or provide more heat to our process of forming a solution, and it's an endothermic process where heat is on the left-hand side of the arrow, by increasing the amount of heat or increasing the temperature, we're going to end up shifting this process in favor of solution formation, away from the addition. So we're going to favor the side where we form our solution overall. So if we add heat or increase the temperature, we're going to also increase the solubility of our solvent or favor solution formation. So this is a very common situation where if you dissolve a solid in a solvent and you warm it up or you increase the temperature, you'll actually increase the solubility of that solute in the solvent. And this is because the addition of heat or kinetic energy is providing additional energy to break the bonds within that solid solute and help it dissolve. On the other hand, we can also form a solution and have an exothermic process take place, or one where the enthalpy of the solution overall is a negative value and the container would feel hot because the process is releasing energy overall. So once again, if we imagine that there's going to be some energy required initially to break apart the intermolecular forces of our solvent when it's separated, and there's going to be some initial energy required to break apart the intermolecular forces of our individual solute, we'll reach that state where we have all of our solute and solvent particles that are separated, all the IMFs between them are broken, and then we can imagine pouring them together and mixing the solute with the solvent in order to make a solution. Now imagine that when we do that, the energy that's released in that solution formation is much greater than the energy that was required to break apart the solvent and the solvent separately. So now we have a release of energy, and our delta H of our solution, the enthalpy of our solution formation, will overall be a negative value because the energy that was provided when we mixed the solute and the solvent together was greater than the energy that was required to break the particles apart. Forming an exothermic solution is actually less common than forming an endothermic solution. So if we imagine we have our solute plus our solvent, and we're going to our product, which is our solution. In this case, since it's an exothermic process, we can imagine heat being generated as a product. Rather, before we saw heat was a reactant in an endothermic process. And so this is going to determine if our solution will increase or decrease in solubility as we increase or decrease the temperature. So now we can imagine our process is trying to release heat because it's an exothermic process. So heat is a product. If we were to start warming up an exothermic process of solution formation and increasing the temperature, we're going to drive it in the opposite direction. So we're going to favor our individual solute and solvent and not favor our solution anymore. Therefore, when you increase the temperature of a process that is exothermic, you're going to actually decrease the solubility because you're moving away from the solution now and you're moving towards the solute and the solvent. So this situation is less common where you're trying to make a solution, and let's say you're dissolving a solid in water and you warm it up, but you actually decrease the solubility by adding heat. So this is because when you're adding heat, you're adding more kinetic energy, and you're actually going to be inhibiting the dissolving reaction because heat is already being produced by this reaction. It's trying to give away heat, and you're trying to give it excess heat by adding some kinetic energy to this process. You may have seen these instant cold packs that sometimes athletic trainers carry. This is a solution that's being made in here that allows this to even work. The packs contain solid ammonium nitrate, which is a salt, and water, and they're both separated in their own compartments. But when you squeeze this instant cold pack, there's a seal between both of them that breaks. And when you shake it up and you mix the two, you form a solution. And so the solution that's being formed is this solid ammonium nitrate is forming aqueous ammonium ions and aqueous nitrate ions. So recall that aqueous means it's surrounded by water. And this process overall is an endothermic process. So the enthalpy of the solution formation is positive, that means. So recall when it's an endothermic process, we can say that heat is a reactant in this process. So we can write it on the reactant side. And that means that the heat is going to be absorbed wherever it can get it. And so if you put this instant cold compress in contact with your body, the heat is going to be absorbed from your body. So we'll increase the heat, which will favor the solution formation. And to you, since it's absorbing heat from you, it will feel cold on you. And it can actually get quite cold and produce temperatures that are less than 0. When thinking about solution formation, it's also important to think about the solubility of the solute in the solvent. Recall from General Chemistry 1, we learned some basic solubility rules for ionic solids dissolving in water. We had common rules like all alkali metals are soluble, or ammonium ions or acetate ions were always soluble, and there were also some common exceptions to the solubility rules. We'll expand upon some of the solubility rules later in class this semester. Solubility can be said to be the degree to which a solute will dissolve in a given solvent, or the maximum amount of solvent that can be dissolved in a solvent at a specified temperature and pressure. So that means that temperature and pressure can also change solubility. The units that are commonly used to report solubility are often the grams of solute dissolved per 100 grams of solvent. This is often used when talking about the solubility of solids and liquids. Sometimes we use the units of grams per liter when we're talking about the solubility of gases in a liquid. The solubility of something will depend upon the nature of the solute and the solvent, the temperature, and the pressure for gases. We've briefly discussed how changing the temperature has an effect on the solubility of solids in a liquid. If we look at the graph on the right, on the y-axis, we're looking at solubility, grams of solute dissolved per 100 grams of water, and on the x-axis, we're looking at temperature. We can see that most of the curves are increasing as we're increasing the temperature, with a few exceptions. This is because usually the general rule is as we increase the temperature of a solution, if it's a liquid or a solid, we will increase the solubility. So increasing temperature typically equals an increase in solubility. And this is because most of those processes are actually endothermic processes where delta H would equal a positive value for the heat of the solution formation. And so heat was a reactant in those cases, and when we increased the temperature, we also favored solution formation, therefore increased the solubility. You can see that this isn't true for all salts, but it's true for most. Here's an example where solubility decreases as we increase temperature. So for this solution formation, the enthalpy must be a negative value, or it must be an exothermic process. That would explain why as we increase the temperature, the solubility decreases, because we're not favoring solution formation anymore. But as a general rule of thumb, we can say that increase in temperature usually equals an increase in solubility when you're dissolving a solid or a liquid in another liquid. Now let's think about how temperature changes affect the solubility of gases, whereas before we were looking at solids and liquids. Gases have rather weak intermolecular forces with water because gases are typically going to be nonpolar, whereas water is a polar substance. So if we imagine we have some gas particles dispersed or dissolved in a solvent like water, they're going to have really weak intermolecular forces of attraction to the water. And imagine what's going to happen if we increase the temperature or we start heating up our gas dissolved in the water. We're adding kinetic energy to this solution by increasing the temperature of it. And we're going to want to break those intermolecular forces and cause some of the gas particles to essentially escape the solution by increasing that temperature. We're helping this process to happen. Therefore, gases are typically more soluble at colder temperatures, whereas they're less soluble at higher temperatures. So a decrease in temperature equals an increase in solubility, specifically for gases. If you do any fishing, you might imagine, where do the fish like to hang out? Well, they typically like to hang out at the bottom of a lake because it's colder at the bottom of a lake. And it's colder down there, so therefore there's more dissolved oxygen in the water for the fish. So a decrease in temperature will equal an increase in solubility for gases because we're having less chances for those intermolecular forces to break between the water and the dissolved gas and less chance for them to escape the solution. Pressure also has an impact on the solubility of gases. Recall that pressure is equal to some force divided by a unit area. So if we imagine we have a gas dissolved in water, so we can say that these are going to be gas particles, and we have a lid on the container. But let's imagine that the lid is some imaginary movable piston sitting above the gas of the vapor. Those vapor particles, which are also a gas, can become more dissolved or less dissolved depending upon how we move this imaginary movable piston above them. Initially, there's going to be an equilibrium established between the number of dissolved particles and the number of undissolved particles. The rate forward will equal the rate reversed. Sometimes a gas particle could collide with the water and become dissolved, whereas sometimes they can collide and have enough energy to escape the liquid solution they're in. One way that we can get more particles to dissolve is by pushing down on this imaginary piston and increasing the pressure of the vapor particles above the liquid. That's going to cause some of these red vapor particles to become dissolved in the solution. Increasing the pressure will decrease this head space right here above the liquid and push particles into the solution. Therefore, more of that gas will dissolve. In general, as we increase the pressure, that equals an increase in the solubility for gases. And after we push down that imaginary piston and let that solution sit for a little bit, a new equilibrium will be restored where the rate forward will once again equal the rate reversed. But now notice there's more particles of gas that are dissolved in our overall solution. The reverse is true as well. If we were to lift up the imaginary piston and increase that head space above our solution, we would see that that would allow for less gas particles to be dissolved. Therefore, a decrease in pressure will equal a decrease in solubility for gases. When you open up a carbonated beverage, that beverage is under pressure, which is causing the carbon dioxide to become dissolved into the solution, usually in the form of carbonic acid. Henry's law is the mathematical relationship between gas pressure and gas solubility. C sub gas equals K sub H times P sub gas, and this is true at a given temperature. C sub gas is the solubility or the concentration of the gas. P sub gas is the partial pressure of a gas over the solution. And K sub H is Henry's law constant, which would be unique to each individual gas. A more common form of Henry's law is C1 over P1 equals C2 over P2, where the subscripts 1 and 2 are referring to some changing conditions or initial and final conditions. For example, if we know a concentration at one partial pressure, we could solve for another concentration at a different partial pressure. Or how will the solubility of the gas change if we change the pressure above the gas? At 20 degrees Celsius, the solubility of nitrogen gas in water is 0.0152 grams per liter when the partial pressure of nitrogen is 585 torr. What will be the solubility of nitrogen in water at 20 degrees Celsius when the partial pressure is increased to 823 torr? So this is an example of a Henry's law problem. C1 over P1 equals C2 over P2. We want to figure out what the new solubility of nitrogen in water will be when we increase the pressure. We can call C1 and P1 whatever we want as long as we're consistent and they go together. we can rearrange and solve for C2 by cross-multiplying first. So C1 times P2 will equal P1 times C2. And then we just have to divide both sides by P sub 1 in order to isolate our new solubility C sub 2. So C2 will equal C1 times P2 over P sub 1. And then looking at our problem, C1 is going to be our first solubility or concentration, 0.0152 grams per liter. And pressure at C1 will be 585 torr. Pressure number 2 is our 823 torr, which we're changing it to. So if we increase the pressure, we should expect an increase in solubility of our gas. That was the trend that we learned. So plugging these in, C sub 2 will equal 0.0152 grams per liter times pressure 2, which is our 823 torr, divided by pressure 1, which is our 585 torr. Our units for pressure can really be anything as long as they're the same so that they cancel out. We learned units of atmospheres, torr, kilopascals, bar, millimeters of mercury. There are a lot of common pressure units for gases, but we just want to make sure that they're the same. Here we don't have to do any conversion because our units are both in torr, and so they will cancel. That gives us a new solubility of 0.0214 grams per liter. So notice our solubility increased when we increased the pressure